Okay, we were talking about association. We'd looked at scatter plots, started to look at scatter plots last time, and we're introducing the idea of association. And I put this scatter plot up that has two sets of parallel lines here. These horizontal ones are at the vertical mean plus or minus 1 standard deviation, I believe, of the vertical variable, and the horizontal lines are, the vertical lines are at the horizontal mean plus or minus 1 standard deviation of the variable that's plotted on the x-axis. So this again is the point of averages. The coordinates of that red square are the average of x and the average of y. All right, so a few things to do here. One is to give you, to talk about something that will confuse some of you when you see it in the homework. So this is a hint. Suppose that these lines had been drawn at plus or minus, at the means plus or minus 2 standard deviation, mean plus or minus 2 standard deviation. Let's think about how many of the points would be in that square, in that box. It's a rectangle. It's not a square. So Chebyshev's inequality would tell us that the fraction of values of x that are in between the two parallel lines that are at the mean plus or minus 2 standard deviations is what? What would Chebyshev's inequality say? It would say that that value is at least something or at most something, first of all. At least. OK, so what's within the range is at least some fraction of the data. And if we're looking at the mean plus or minus 2 standard deviations, what fraction would need to be in that range? Two-thirds. We have a vote for two-thirds. Sorry? We can say two-thirds is true, but we can say more than that. It's actually some number that's even bigger than two-thirds. 75%. I like 75% better. OK. The amount that would be beyond 2 standard deviations away from the mean is at most 1 divided by 2 squared, right? 1/4. So the amount that's outside is at most 25%. The amount that's inside is at least 75%. OK? Now let's suppose that we had this box was the mean plus or minus 2 standard deviations in this direction. What fraction of the y values would need to be between those limits? Again, the fraction that would be beyond 2 standard deviations is at most 1/4. 1/2 squared. The fraction that's within is at least 3/4. Right? So if the fraction of x values that are in this range is at least 3/4 of the x values, and the fraction of y values that are in this range is at least 3/4 of the y values, what fraction of numbers must be in the box, in the whole rectangle? Sorry? There is a homework problem not unlike that. Sorry? 9 over 60? 16? 9 over 16? So you're going 3/4 squared? Is that what? So 75% of 75%? OK, there's one vote. Anybody want to get behind that or propose something else? Or? All right, so if these lines had been drawn at plus or minus 2 standard deviations, plus or minus 2 standard deviations away from the mean, then we lose at most 25%. We lose at most 25%. How much is left in the middle? So the claim that what's left in the middle is 3/4 of 3/4 is kind of saying when we throw out that stuff, we lose at most 25%. And when we throw out this stuff, we lose at most 25% of what's left. Right? Yes? 1 minus 0.25 squared. OK. That would be an even bigger number than 0.75, right? So let's just, the proposal is maybe the answer is 1 minus a quarter squared. So let's think, if we lose, if after we throw out that, what's left is at least 75%, but not necessarily 80, not necessarily 90. When we throw out this, we've got to be throwing out something more. So the answer when we throw out this needs to be somehow less than 75%. But if 1 minus 0.25 squared is bigger than 75%. So you're sort of saying that you're throwing out less. So that doesn't pass a sniff test, as it were, right? It's sort of, the number ought to be less than 75%. The question is how much. Does that make sense to everybody? OK, so the claim that what's left is at least 75% of 75%, right, at least 0.75 squared, is saying that when you throw out this, you lose 25. When you throw out that, you lose at most 25% of what's left. Okay? Does Chebyshev's inequality sit? For that to be true, what will we need to be applying Chebyshev's inequality to? Right? We start off with the standard deviation of all the y values. And if we want to say that when we throw out what's beyond 2 standard deviations of all the y values, we lose at most 25% of what's left. The argument is a little bit more subtle, right? It would be true if we were looking at the standard deviation of the y values that are left after you throw out the points that have extreme x values, right? Throw out some points, look at what's left, take the standard deviation of the y values of what's left. If you then threw away what was beyond 2 standard deviations of those remaining things, you'd be throwing away at most a quarter of those remaining things. Okay? But that's not what the story is. We're using the standard deviation of all the y values, not the standard deviation of the y values that are left after you throw away those x's. Okay? So all you know is you lose at most 25%, you lose at most 25% of the whole each time. So all you really know is that what's left is at least 1 minus 25% minus 25%. What's left is at least 50%. Okay? In order to say that what's left is 75% of 75%, you would need to know that when you throw away the extremes, you're only throwing away 25% of what's left, not 25% of the whole. That would be true if the standard deviation of what was left of the points, if you you throw away the values of x that are out there, and now you just look at these points that are in the middle, you take the standard deviation of their y values. And now you exclude everything that is more than 2 standard deviations of those, right? Not of the whole, but just of those. Then it would be 75% of 75%.